Okay, we're very happy to restart MOPA for this semester, and this semester we have an abbreviated session, a schedule where with three talks coming up, and a special session in about a month to honor Jim Schmerl. So we'll start our session, our semester this year with Ermek Nurkhaidarov speaking on automorphisms of countable short recursively saturated models of PA. Go ahead, Ermac.
Uh, Thank you for an opportunity for present at the MOPA. It's been a while since the last time I was, and I wish we were maybe in person, but I guess it's more convenient for us to do it on Zoom. The project which I'm presenting here is the joint project we were doing with ERAS, and we hope to be able to finish our writing out our paper about that by May or something like that. And I will do the first part of the talk, and ERAS will do the second part. And technically, it's supposed to be actually the other way around. ERAS was supposed to be doing the first part, and I was doing the second. But there are like some meetings I have to attend next week, and I'm not sure if I will be able to do that. Anyhow, thank you again, and let's start the talk. In this talk, we're going to be studying the properties of automorphisms of countable short recursively saturated model of Peano arithmetic. It is one of the questions which we'll asking when we study automorphism group of models is how much information about the model itself can be recovered from its automorphism group. There are a number of, by now, I guess, classical results which is known about the automorphism group of countable arithmetically saturated model of Peano arithmetic. In particularly, Roman and Jim in their 95 paper proved that the automorphism group of a countable arithmetically saturated model of PA caused its standard system. Using this result, they proved that if M1 and M2 are countable arithmetically saturated model of arithmetic, and if they have the same standard system, then they should have the same standard system. I mean, if their automorphism groups are isomorphic, then they should have the same standard system. Another regard in this direction is I was able to show that, again, if M is countable arithmetically saturated model of Peano arithmetic, then automorphism group of M can recognize if a maximal open subgroup is a stabilizer of a non-standard element, which is smaller than any non-standard definable element. Basically, we were talking about something like about the elements from a small disinterestedness. And that result is used to show that if a previous result is talks about, if Roman and Jim result talks about that model called standard system, then this result talks that what little bit can be recovered about where some little bit information can be recovered about the model. I mean about the theory of model. So, and this result is used to show that if M1 and M2 are countable arithmetically saturated model of Peano arithmetic, such that where automorphism groups are isomorphic, then for every n less than omega, we have at omega with representation of theory of first model if it proves RT2n, and if and only if omega with representation of second theory of second model proves the same RT2n. Here, RT2n stands for infinite times theorem. What we'll do in this talk, we'll try to outline similar results for short arithmetically saturated model of Peano arithmetic. So at least that's the goal, and we'll see how it turns out. So I'll start with a couple of definitions, and then I will try to at least outline how our proof might work and what's the difference between what was proven for tall recursively saturated models versus short. So some basic notation which I'm going to be using. If M is a model of Peano arithmetic, I'm going to be using capital G for its automorphism group. If A is subset of M, we're going to use the following two notations. The first one for a point-wise stabilizer of A, and the second one for set-wise stabilizer of A. We're going to introduce the topology on the automorphism group of M, and the basic open subgroups are going to be point-wise stabilizer of finite sets. So that is a standard topology on automorphism group. And also we define the standard system to be a subset of omega which are coded by definable elements in M, and representation of T is subsets which are coded by the prime model of T. Okay. Definition of a recursively saturated model. So we say model is recursively saturated with realize all the recursive types, P of X, A, where A and M. Model is called arithmetically saturated if for every arithmetic type, if every arithmetic type over type of A is realized in M. The next kind of theorem will provide a little bit insight on what our arithmetically saturated models are. Before that, I will define what is a strong cut. So we say cut omega is strong in M if for every A in M there is C bigger than omega, such that for every I in omega, standard I, AI is in omega if and only if AI greater than C. Then Kirby in 1984 proved that if M is countably recursively saturated model of Peano arithmetic, then the following equivalent: M is arithmetically saturated, or if and only if omega is strong in M, if and only if omega with standard system is a model of ACA0. So a little bit introduction on arithmetically saturated models. Now we'll try to define the short models. We start with defining the bounded type. So we have type is bounded if it contains a formula which says that basically V is less than T of A. Basically says that, element is not unbounded because we have a formula V less than T of A. A model M is short recursively / arithmetically saturated if and only if M is not recursively saturated and every bounded recursive type is realized in M. So you notice that there is also definition of bounded recursive saturation, but here we're going to be talking about short recursively saturated models, which are like really short, not tall. Next theorem, which was proven by Smarinsky, provide a little bit of insight of what is going on with short models. So basically the situation is the following. So if we have a short model, then basically we can think about short model as if we have short model, they can always think about M short model as like a initial cut, elementary initial cut of a recursively saturated model. With so that there is like a last gap sitting somewhere here. So that's how we can think about that. So if M is model of PA, and A belongs to M, we define what M of A is. So M of A is essentially the smallest elementary cut which contains A. And then Smarinsky proved that model N is countably shortly saturated if and only if it is isomorphic to M of A for some recursively saturated model of M with A belong, if A and M. So that's picture. So we can think about short models as initial elementary cuts with a last gap of element A. So something along these lines. Let them be countable recursively saturated model of P when we can define invariant cuts. So we say I is upward invariant if there is a sequence of definable elements in M which are upward cofinal in I. So the situation kind of looks the following. So we have I, which sits inside of our model M, and it's upward invariant if there is a sequence of definable elements which is upward cofinal. So sequence of elements which is going toward I. That's upward invariant, and we also can define downward invariant, saying that similar picture, but we have a sequence of definable elements which are going downward toward I. And we say cut is invariant if it's either upward or downward invariant. It's not difficult to see that if I is invariant cut, then automorphism group of M, which takes an I pointwise, is a closed normal subgroup of automorphism group of M. So that is a definition of invariant cut for tall models. For short models, we have to adjust that definition slightly, and it might sound something. Okay, firstly, K showed that the inverse of previous statement is true, that if M is countable recursive saturated model of Peano arithmetic, then subgroup is closed normal if and only if it is in the form automorphism of M which fixes some invariant cut I pointwise. So basically, K's theorem says that we can recognize there is like one-to-one correspondence between closed normal subgroups and invariant cuts. RS did a similar results for short countable recursively saturated models, but the definition of invariant cut has to be tweaked a little bit. Let M of A be a short countable recursively saturated model of PA. If I is then cut in model of A, we say I is invariant if for every automorphism G, if every automorphism G fixes I setwise. So you see that's a little bit, for that definition is equivalent for tall models, for recursively saturated models. It's equivalent, but that is the definition, that's a correct definition for short models. The reason for that is when we're talking about short models, there is opportunity that we will have our M of A here, and then A sits here, and then that cut I will be invariant, but it doesn't have to be coded. It doesn't have to be downward invariant or upward invariant. That's why we have to twist the definition. Again, it's not difficult to see that if I is invariant cut in a short model, then automorphism group of M of A of a short model which fixes I pointwise is closed normal subgroup.
Can I ask
Yeah.
something here? If you throw in a as a parameter, does that like as an extra constant, um, then I here would be the infimum of of that gap, right? And so would that if you consider it from that perspective of essentially the same definition you had before, but not using definable elements, the using elements that are definable from A, like elements in the skull enclosure of A, would that give you the same notion of invariant cut as what you have here?
Uh, it is kind of so the situation is kind of a following. So we kind of we have M of A, but M of A might have like different names. It can have like names M or M of B. So basically, like we
Mm.
pick an element from that gap,
Hmm.
and the problem might arise when we might have element of a rare type, so like distinct, and we can separate it.
Hmm.
Or we might have a situation where like indistinct elements, like there is like a and there is like the element a1 which is of the same type as a, and that basically will leave like so-called unlabeled gaps, so there is no
I see.
label for it.
Yeah.
And that's why that's kind of gap to define invariant cut,
Right.
but at the same time there is no parameters unless we like really force it and add that to the language.
Okay.
And Eres in his talk will be talking more about that. He will be talking about what is happening in the last gap. If we have like rare elements, if it's like non-labeled gap, if it's like quasi
Hmm.
quasi selective. So yeah, Eres will be talking more about that. And as I mentioned earlier, the order of the talks should have been like Eres doing the first one and doing the second one, but yeah, it happens that I have to go first.
It's okay. All right. All right. Thank you.
Okay, yeah. So basically, that's basically why we have to put that definition slightly different for short models. Okay. So, and as I mentioned, RS proved that for short countable recursively associated models of Peano arithmetic, the converse is true that if we start with short countable recursively associated model of PA, subgroup is closed normal subgroup if and only if it's in the form of which is a pointwise stabilizer of invariant cut. So again, if we have the automorphism group with topology, then we kind of have access to those invariant cuts. That's basically what that theorem says, and that's how we're going to be using that. So we're going to be thinking that if we have topological group, then we can recognize invariant cuts. If M is model of Peano arithmetic, it can be short, it can be tall. We define omega to be the set of all elements greater than the standard cut and smaller than any non-standard definable elements. If omega is not equal to 0, not non-empty, then it is called the smallest injustice. So basically, when we're looking at the models of Peano arithmetic, we can think about them as we have like our standards element here, then we have our non-standard definable elements, and then we have potentially unbounded elements or maybe bounded depending on whenever we're working with short or tall models. And the smallest injustice sits somewhere here, sits between standard elements and non-standard definable elements. And it follows from the from a correspondence between invariant cuts and closed normal subgroups that if we're going to fix the smallest interstices pointwise, that corresponds to the largest closed normal subgroup of non-trivial of automorphism group of M of A. So we kind of, to an extent, we can recognize what is the smallest interstice if it's not empty. And that's what we're going to be using at some point. The next few statements will be talking about the something similar to so we work inside of interstices, and we try to define interstitial gaps, and that's what the next something equivalent to your regular gaps. That's interstitial gaps, and that's what we do in the next few definitions. So if it doesn't have to be the smallest interstice, it can be the similar definition can be given for any interstice. So, for example, we can define the same thing for like our regular gaps. But anyhow, if omega omega is non-empty, we define a set of functions, say R, which is to be definable functions, and they have to be non-decreasing, and they should be moving elements from smallest interstice to element of smallest interstice. And then we define interstitial gap to be a set of elements which are on the same level inside of our interstice, in the same level in terms of that set that function. So we'll say that if we have an element A here, element A here inside of our omega omega, right? Then we can consider a set of elements which are which can be moved higher than element of A, with element FA, using that set of functions, and that's kind of going to be our interstitial gap. So basically, like if you start with A, you can go back high, and starting with element B, you can go to the same height. That's what means by going to the same interstitial gap. So again, somewhat similar to definition of a gap. Okay, and now a couple words which I wanted to mention about how that proof of Jim and Roman paper goes, and how we'll translate it into our case. So for Jim and Roman, we're using M to be countable, recursively saturated. Model of K. So the picture looks like this, and then we have definable non-certain elements, and the way we did were proofs with unbounded elements. So we did the proof with regular gaps, and we did use access to indiscernible elements. So basically we did all the proof here. So we did the proof for using unbounded elements, elements of unbounded type. When working inside of, so that's Cossack Jim. So we did the coding inside of that so-called like last interstice or biggest interstice, largest omega omega. So we did it omega infinity. So we did fair proof here. We did coding there. So when we're talking with M of A, that is countable short, recursively saturated. Situation is different. It might be similar. And Erez will be talking about that in his talk. He will present like what is going on with the last gap, what is my potentially with I don't remember what's the name for tail inverses. So anyhow, we kind of have, that because we're working with bounded types, so we basically have like our bounded, so we don't have like that clear access to unbounded types, and we don't have access to that omega infinity. So what we do instead is we will try to do the same kind of coding with potentially with some restrictions, and instead of working with unbounded type elements, we're going to be working with opposite, like almost like opposite, like we're elements of from omega, from the first interstice, from the smallest interstice. So we'll try, what we do, we try to translate all the proofs for the elements which we did for largest interstice, we'll prove it for smallest interstice. And that's going to be our idea, and that's how we're going to proceed. And during that work, we, instead of working, say, with moving gap, where a lemma will be moving its equivalent to interstitial gap lemma, and so on and so on and so on. And that's an idea. Okay. So for the rest of the talk, we're going to fix M of A to be countable short recursively saturated model of Peano arithmetic, and G of A to be its automorphism group. The next couple of definition is going to be somewhat similar to the definition which is given by Jim and Roman in their paper. First one, we will definition of precede. We say that subgroup, if given to subgroup and H and K of G of A, we say H precedes K if conjugates of K by automorphism H from H is a subgroup of G of A which fixes the first interstice pointwise. So what that definition is trying to catch, it's trying to catch and say something along the lines that if H is setwise stabilizer of I, of cut I, and K is setwise stabilizer of cut J, then this definition will basically say that I is a subset of J. At least that's like intuition behind it. Otherwise, it's a little bit like confusion what is going on here. Next definition says that if we have a subgroup H of G of A, we define two subgroups of G of A. H sub star is the intersection of all conjugates of H which precedes A, which precedes H, and H superstar is the closure of subgroups generated by the union of all K substar where K is conjugate of EH which is preceded by H. So what we're trying to do here is kind of, so if again, if we'll look at a particular group, and if H is on the form G, which is going to fix I setwise, then we will look at I kind of the following way. I sits here and keeps on going. Then H substar will try to catch all their, basically will try to fix pointwise potentially up to I elementary cut or I cut or some cut, and H superstar will cut a little bit bigger than I pointwise. I mean, that's kind of kind of what we're trying to grasp. Okay. We also have to define like special groups we wish to have in our automorphism group. We're going to call them nice. And their properties are listed here. So again, what we're trying to do here is we try to say that H is a stabilizer of element which H is a maximal subgroup, and H is in the form of that which is going to fix I set Y. So we've tried to catch that kind of and that's why we try to give a definition here with some extra condition that to be maximal open subgroups. That's like kind of technical because that's what we kind of start with, because that's somehow easier to get to access to some elementary, in our case, ICATs. So that's kind of a little bit forced. That is similar to what Kotlarski introduced. That's basically somewhat similar to what Kotlarski did. Second condition is because we want to be working inside of our smallest interests, so we want to make sure that we have our omega omega and our ICAT will be sitting inside of omega omega. That's why we have the second property. Okay, and properties 3, 4, and 5 are a little bit technical just to help us to do the proofs. Some of them might be like, a little bit excessive. Maybe we don't necessarily have to have them, but it's kind of easy when we have them. So just to avoid like easy to do proofs. Okay, that's an idea behind that. And the next few lemmas will basically say that, that is a correct definition. That is, if you define a nice group this way, then it actually is in the form which is going to fix some ICAT set-wise. And basically, if you look at the definition which is given here, then we will be basically able to catch all the nice subgroup if they exist, because that is kind of in the sense if we have access to isomorphism group and automorphism group and to its topology, when they can see which subgroups are nice. Okay, so as I mentioned, the next lemma is saying exactly that. If H is subgroup, then it's in the form of set-wise stabilizer for some ICAT from the smallest interstices. Then the next lemma will say that, that the definition of which we precede works well on the nice subgroups. We can think about nice subgroups which are going to be fixing I and J to corresponding ICATs. Then H precedes K means I precedes J. So we kind of now have access to our interstitial gaps, and then now we also have to access to our their ordering of ICATs. And then we all basically have access now to interstitial gaps as soon as we get that. So next lemma says that let H be a nice subgroup if H is in the form which is fixed in some J setwise, such that J is not equal to the primum for any I gap, then H substar equals to pointwise stabilizer of J. So basically, what we do is we can get access to interstitial gaps now, and then using the case theorem, we can recognize the difference between using case RS theorem actually, which is somewhat generalization of case theorem for short models. We can see the difference between when the interstitial gap is labeled or not labeled. So that's basically what the next theorem is kind of saying. From previous lemma, we can access to gaps, and in this theorem, we can distinguish the difference between labeled gap, where gaps which will have interstitial gaps which will have rare types elements, versus gaps which will have no rare types elements. Because again, same type of picture, if we have our gap, if it's not labeled, then basically your H superstar will fix this cut, and H substar will fix that cut. And then depending on whenever we have labels in the side of a D or not, we might have invariant, we might have closed normal subgroups sitting here or not. So if we have like rare type elements sitting inside of D, then we're going to have some extra access to some closed normal subgroups inside of H here. So that's kind of how we can recognize, at least that's like intuition behind. So from this one, it follows that we can, that model, I mean, that's automorphism group of our countable short recursively saturated model of Peano arithmetic as a topological group can recognize if a nice subgroup is a stabilizer of non-standard element, which is smaller than any non-standard definable element. So basically, we can recognize if subgroup is a stabilizer of element from if a nice subgroup is a stabilizer of an element. So we have access to that. And after that, we'll move on to a few more definitions. Basically, what we try to do is kind of get access or try to define a couple of special groups. And those special groups will basically corresponding to indiscernible elements. So we'll say that H is indiscernible subgroup. Firstly, H is nice. Second is a stabilizer of a point. And third, it's basically saying that, you know, somewhat similar to be indiscernible elements. So we'll say the same for indiscernible kind of subgroups. So we'll say if H1 through Hn and K1 through Kn are subgroups isomorphic to H, such that Hi precedes Aj and Ki precedes Kj, then we can find G so that the whole sequence H1 through Hn and K1 through Kn are kind of isomorphic. In this case, we'll say conjugate to each other. Then we give definition of indiscernible elements, like our regular definition of indiscernible elements. And indiscernible element, we say B, which is from the smallest inserts, its type is n-indiscernible if B is non-definable and for every A0 from an minus 1 and B0 for Bn minus 1, such that they are of type B. If that's happening, then type of sequence A is the same type of sequence B. So somewhat standard definition of definable elements. Then we show that there is like one-to-one correspondence between n indiscernible elements and n indiscernible types from the smallest inserts. So let H be a subgroup of G of A, then H is n indiscernible if and only if H equals to G of B for some B from the smallest inserts, such that type of B is n indiscernible. So, and as a corollary from that, we see that indiscernible types are recognizable. So that's what corollary. Let H be a subgroup of automorphism group of M, then the topological group automorphism group of M of A recognize if H is in the form G of B for some B such that type of B is unbounded and it should not be unbounded and indiscernible. So I mean it's from the small inserts. That's what's supposed to be here. So they recognize that. And then combining that, we can get the following result. So let M1 and M2 be countable short arithmetically saturated models of PA. If M1 and if automorphism group M1 and automorphism group M2 are topologically isomorphic, then for every n less than omega with representation of theory of M1, proof representation of Ramsey of T to n, if and only if omega with representation of theory of M2 proves RT to n. So basically, the picture kind of goes the following way. So let me try to maybe to sketch that. So if we start with B from omega with the smallest interest, then type of B is n indiscernible. That is equivalent that there exists some corresponding H, which is going to be fixing B pointwise is n indiscernible.
Right.
Yeah.
So we've been very quiet all the time. So but you didn't say at any point so far that those things exist, did you?
About existence?
Yeah.
Because we're talking about here, right? About countable arithmetically saturated models. So because we're talking about arithmetically saturated models, that it's implied that our smallest interest is not empty.
That's
so
right.
I need to have
but now existence of those and like about existence of two indiscernible types.
Yes,
how do we know that?
And I need to yeah. Okay, and for that, I need to add that property which I have it here, extra property that it's proof RT to n, that it proves a Ramsey statement.
Right. So the existence of those indiscernibles will follow from Ramsey, and then it's equivalent to existence to the subgroups that nice subgroups.
Yeah. So that's why I kind of have like three equivalences which I kind of trying to put together. So if we have like type of B and n indiscernible, that is equivalent to saying that omega is representation of theory of T, right? Of T, I guess.
All right.
Proofs are I don't remember where I put the index, 2n.
Mm-hmm.
Yeah.
All right. Thank you. Thank you.
So that's why we need slow. I wrote it already. It's kind of not there. That's interesting. Do you see that last equivalency? Okay, so anyhow, we have like those 3 equivalences. Okay, so we have those 3 equivalences. And that's kind of what's kind of will go. So we have like n indiscernible subgroup, and n indiscernible subgroup is equivalent to n indiscernible element. N indiscernible element corresponds to that property that omega representation proves some statement about Ramsey. So that's kind of what we need to have, like those like equivalence, and that's why we have that theorem, because topological group recognize if it has an indiscernible subgroups, which is equivalent to n indiscernible elements, which is equivalent to Ramsey statement. Okay, I hope that makes sense, some sense. Okay, that was the first part about, and next part is going to be very similar to what Roman and Jim did. So basically, if we have access to those special nice subgroups, there is like a theory in which if omega is not non-empty, we always, if the small situation is not empty, we have access to them. So if that happens, then we can recognize if H is stabilized with label gap. Label gap means we have label I gaps. That means we can recognize, we see the difference between gaps with rare types and gaps without rare types. Then the next definition is exactly the same basic definition as Roman and Jim did. The only difference is somehow I put like extra requirement that HI to be HI to be 2 indiscernible. I believe in the Jim and Roman paper it was just selective, maybe not 2 indiscernible, but otherwise it's basically the same definition. We say if we have given subgroups K, H0, H1, and so on of G of A, we say K supports H0, H1, 2. The following holds: K is a stabilizer of the labeled I gap. HIs are 2 indiscernible and nice. I guess I need to put like extra nice here. I just want to be at least for this, I guess, talk, we already assume that indiscernibles are nice. We'll assume that HI and J are isomorphic, and K is subgroup of HI for each HI, and if K is subgroup of H, then H is already one of those subgroups which already there is nothing more. So in a sense, we can think about that K is element which is going to code elements A. If we can think about that, like K is G of B, then you can think about H of 0. It's like G of A0, G of A1. And then you can think that B will code it like B0 equals to A0, B1 equals to A1, and so on. That's kind of an idea behind that definition. And then we will say that X subset of omega, then G of A in cos X, if either X is finite or X equals to I0 through IN, where I0 less than I1 through less than I2. And there are subgroups K1 and K2, H0, H1, and H2 of G of A, such that K supports all H, but K2 supports only the particular ones which corresponds to that set X. And the theorem will say that, well, if M countable short arithmetic research, M1 and M2 are countable short arithmetic research models of Peano arithmetic, we need to have an extra requirement and access to our indeterminable elements. So that's why we have that requirement that omega representation theory of M1 proves RT22. In their paper, Jim and Roman were working in their largest universities, so they had access to those indeterminable elements for free. So, but we don't have it, so we have to put that. If automorphism group of M1 and M2 are topologically isomorphic, then they should have the same standard system. And thank you. That is what I wanted to be talking about, at least for this talk.
Okay, thank you, Ermek.
Thank you. Now, where is this? React. Oh, here it is.
Yes.
Thank you.
Are there questions for Ermek?
So, okay, Vika, go ahead.
No, I don't have a question, just a remark. Galois is very happy in heaven.
Sorry, I couldn't hear that, Ken. Can you go ahead? Can you say that again?
I'll try it again. Yeah, Galois is very happy in heaven.
Well, he's constantly happy, I think. That's true. That look, but there is no word on the small index property.
No.
Not even next week. So RS will not tell us that GA has a small index property.
So if I try to spoil what RS will be talking about, he will be talking, if I understand that correctly, he will be talking about MA. So he will try to concentrate on what is happening here in the last cup. And potentially, if we have like where one before it, if it's like labeled, not labeled, quasi-selective and stuff like that. So.
Yeah. No. So this, my paper with Jim, this is all ancient history. This is actually 30 years ago. So the details I murky, but I wonder if there is any use, because in the book we have this nice example, and is due to Jim, that for unbounded types, 2 indiscernibility already implies indiscernibility. And then you get all those maximality of open subgroups, but and all of those nice properties. But Jim has a nice example of a 2 indiscernible type that's not 3 indiscernible, actually a construction for every n of a bounded n indiscernible type that's not n+1. And I wonder whether they other than being interesting examples, maybe they can be used somewhere here to tell difference between some models and some groups based on that. Because you in your theorem, all you need is 2 indiscernibility, which is actually nice. But what if you have more? Can you get more? Can you say something more specific, maybe of the theory that that representable sets something instead of this?
Yeah. So for example, here you can potentially have like one which is model of 2 versus one which is model of RT23, right?
Things like that, right?
Versus one which is not model of RT22, right? Yeah.
Yeah.
Yeah. So you can potentially get a few models here, and Jim was able, as soon as he got here, he was able to do some construction of theories which will use that kind of properties to do some result and some, so that there are like infinitely many theories which are going to have the same standard system but not isomorphic. So I believe
groups.
I believe you can do the same thing and for short models and can kind of prove the same thing.
But that would be nice, but tedious, I guess.
Yeah, but it should. I think it should be more or less automatically transferred here. But it's kind of interesting to see. It's like as you were saying, there are like two indiscernible which are not three indiscernible, like three indiscernible which are not four indiscernible, and so on and so on. It's kind of nice. At some point, I believe I and Jim were thinking, trying to do like codes using like those like rainbow indiscernible elements, like with like model will have like some kind of indiscernibles, but somehow we were not able to get anything but going that.
I see. Yeah, it's a pity Jim couldn't be here today, but maybe he'll be here next week.
Any other questions for Ermek?
And potentially that's what, again, Erez will be talking about. We might have access, say, if we have like a non-labeled last gap, we might have access to these interstices, right? And we can do like coding in that interstice without a requirement, that we need to have RT22 for omega representation stuff. But it all depends on what RS will like. Is it quasi-selective types or something? But it really depends on what is going on with the last gap.
All right.
Okay, great. All right, so let's thank Ermek again. Thank
you, Ermek.
Thank you.
Thank you.
Yes, and as Ermek mentioned, next week Erez will speak, and the details will be posted online. It's probably later this week, but he just sent me the title. It says "Invariant Cuts of Countable Short Recursively Saturated Models of Arithmetic." So, sort of continuing on the same project that Ermek was speaking about. All right, we'll see you all next week.
Okay, see you next week.